So we finally gotten through all the stuff about what a stress tensor is, what you can do to manipulate it, how you go from stress to strain and vice versa, and we're done with all that. Well, I mean, it's going to come up in we're done bringing up new things with that, and now it's going to come up in every problem we do. But for the rest of the class, we're going to be talking about how to calculate the stress in a real situation. Right now we've just been talking about these abstract things that are stress tensors at a point, drawing stress elements, that kind of stuff, talking about strain at a point. So now finally, we're going to get to stresses due to actual loads on actual objects, and that's going to be most of the rest of this class. And I'm going to break it up into two pieces. The first one is going to be short and easy and minimal. But the first one is objects that are loaded like a big stress element. I don't know, I don't have a better way to say that. But that's what we'll talk about today. And then after that, we'll talk about beams. And when we talk about beams, this will go from external loads which will a lot of times come from statics problems, and then we'll go from that to internal loads. Not everybody gets that in statics. People who took statics from me did, but we'll go over that again. And then we'll go from that to stresses. And then once you have the stresses, you can calculate the principal stresses, the maximum shear stress, the strains. You can re-express these stresses in new coordinate systems, all that stuff that you know how to do. So, okay, so the first one. Objects, I'm really going to write this again, I guess so. Objects loaded like a big stress element. Okay, and what I mean by that is they have to obey all of the rules that are required for a stress element. You know, for example, if you had, well, I'll get to that. All right, so I think the easiest way to show this is with an example. So let's say that we had a big bar with a square cross-section. The height, let's say that's 0.2 meters. The width is 0.2 meters. That's what makes it square. Maybe some things are starting to come together for you now. And the length, let's say it's 1.5 meters. And let's say the loading is like this. I'm going to draw just straight front view for the loading. This is the coordinate system. And so let's say that everything's distributed loads. And we have a total force of 20,000 newtons on the right going that direction, a total force of 20,000 newtons on the left going this direction. And then we have a distributed load in this direction along the top. And those directions on the other faces. And the magnitude of all of those is oh, I didn't think of that. Well, let me give that as a traction. So let's say that that's equal to 10,000 newtons per meter squared, all those shear loads. Okay. So what are the stresses, the stress tensors for points in this bar? Well, the way you do this is divide the total force by the area of the loaded face. To get the traction vector on that face. And then once you have the tractions, the stress tensor for every point inside that body is just going to be the same as it would be for that stress element. So for the two tensions, that XX stress is going to be 20,000 divided by the area of that face is, nope, just 0.2 yet. 0.2 times 0.2. So what do you get? 20,000 divided by 0.04. What? What is it? Is that all? 5? No, 5 million. Right?
No, 500,000.
Damn. That's low. Okay. And then, well, the way I did it, these are already given as tractions on the other faces. So the XY stress is $10,000 newtons per meter squared is pascals. And so every point inside this body has a stress tensor that's equal to 500,000, 10,000, 0, 10,000, 0, 0, 0, 0, 0 pascals. Okay. So you can use this approach for any object that satisfies the requirements for a stress element. Okay, so what if you have,
On that last one,
yeah,
what did all the arrows represent?
that just represents that instead of there being one point where that total force is applied, this is applied as a distributed load. Like it's applied by something, pressing down on the whole surface and pushing to the right.
Oh, okay.
And so that's something we're going to have to deal with too, is how these, because how often is it going to happen that all these forces, even if the forces themselves would satisfy the requirements of the stress element, how often are they going to be distributed uniformly like that along the top? And we have to take that into account too. Okay, so now how about, say we have a column like this with a length of 1 meter, 0.1 meters, and a cross-sectional surface with a radius of 0.01 meters. And the loading on the two ends is 5,000 newtons distributed uniformly over the end. What's the stress tensor? I guess I'll use the same coordinate system again. Well, this isn't shaped like a stress element, but the only loading is on the positive y and negative y faces. And so the YY stress is equal to, this is compression, so you have negative 5,000 divided by that cross-sectional area, which is pi times 0.01 squared. What do you get if you divide that?
Negative 1.59 × 7.
Okay, pascals. There are no loads on any other faces. And so the stress tensor is 0, 0, 0, 0, negative 1.59 times 10 to the 7th, and then zeros everywhere else. And so what happens if the loads those external loads aren't uniformly distributed? That's obviously going to happen pretty often. So what if those external loads aren't uniformly distributed? Most of the time that's going to be the case. So what's the principle that is relevant for something like this?
I'm just asking for stress tensors, so I mean,
Uh-huh.
can we draw the stress
Remember when we had that discussion about principles and like Saint Venant's principle? Yeah. Yeah, but it's not supposed to have been a week since you read your notes. Yeah, it is always in the daily assignment.
Yeah, so we all did read it.
Oh, I see. Okay, yeah. I thought you were saying, well, it wasn't in the dailies. Okay. Okay. Principle, PLE. And so St. Venant's principle says you can treat the material as if it was a uniformly distributed load that was being applied, as long as you don't trust your answers too close to where that load is applied. So here's an example. So let's say that we had this bar. For some reason recently it occurred to me that like it just popped into my head that when I say bar, that I could be saying like bear, like a person from like Montana or whatever, and now that's what always I feel like I'm, yeah, like you wrestled a bar. I don't know, it's really stupid, but I can't seem to get that out of my head. Talking about it now isn't going to help. Okay, so let's say there's like, you have this bar with 50,000 newtons applied as a point force there, and 50,000 newtons applied as a point force there. You can treat this as this, you know, where that's a uniformly distributed load, that's a uniformly distributed load, where the magnitudes are still equal to 50,000 newtons. As long as you don't pay any attention to the results that it suggests in that region and that region. Okay, so if we had those dimensions, we could do this the same way that we did the other ones. We just, in the other case where you have a uniformly distributed load, this is the stress tensor at every single point in that material. In this case, this is the stress tensor pretty accurately at every single point once you get as far away from the end as the end is long in its longest dimension. Okay, so why don't you want to trust the ends? I have one little example that shows what happens. So this is a finite element calculation. Remember, finite elements I mentioned before is like a numerical approach to doing deformed problems. It's what you use in any real world application for the most part. So this is the bar that I just drew as an example. So this is with uniformly distributed loads being applied at the two ends, okay? And so you expect, and we can think of this as the true results, okay? So just like I said, the true results say that every single point in that bar has, stupid bar, has the same exact stress tensor, right? And that's what you see there, that the blue says, that color blue, that tells you, I'm not going to go into what this measure of stress is, but it's basically an index of stress that takes all the stress elements into account and represents it as a single value. And so blue says it's the same value everywhere. Okay. So now let's see what happens when you replace that uniformly distributed load with a point force here and a point force at the opposite corner. What do you think is going to happen? That's exactly right. It's going to be a very high stress at the locations where those point forces are applied. And then over a small distance, it's going to fade into being in the middle. Once you get away from the ends, it's going to be blue everywhere again, as if it was a uniformly distributed load. I hope. I haven't looked at these pictures yet. Yes. So you get the stress concentrations where the point load is applied, and then as you get just about the length, so consider the length of this diagonal on the loaded face. When you get just about that far away, it's back to the same stress that we predicted with uniformly distributed loads.
Very nice now. So, nice looking. I think it's
That is weird. I'll bet that's more a numerical effect than a real. Like if you really did the true elasticity calculations, these would be partial differential equations, and I'll bet it would be smooth. Yeah, and if I would have broken it up into more elements and let it run overnight, I bet it would have looked smooth, Yeah. So one thing to keep in mind with this notice this approach only works if the object, let's say, if the object's loads satisfy all the requirements of a stress element. Well, it just means that the opposite normal tractions on opposite faces have to be equal and opposite, and the shear tractions have to do the things that you need for that tensor to be symmetric. Okay, so
that one matches that one.
right, yeah, that thing. I don't have a good concise way to describe that, but that thing, yeah. All right, so here's an example. So what about this?
Some example of one that won't work.
Yes. You can't use this approach on this example because that normal stress, let me give a value for this, I don't know, 5,000. Because that normal stress that's being applied to the, or that normal traction that's being applied on the top surface doesn't have a matching one on the bottom surface. Okay. Bless you. Same thing with if you have an object like this, where all you have is a single external load applied that way. Let's say that's 10,000 newtons. This approach doesn't apply because you couldn't have loading like that on a stress element.
What exactly is happening in that?
What's wrong with that? That's like you have a something is pushing towards the wall on this box on the top,
But you don't have the ones.
but you don't have the matching ones going that way, and that way. So it doesn't meet the requirements of a stress element, so you can't assume that the stress tensor is going to have, you can't assume that, like in this case, the yx element of stress is going to be equal to 10,000 divided by the area. You can't do that.
Practically speaking, like, could that happen? Like, wouldn't that cause
Well, I guess unless this is going to accelerate off to the side really fast, you'd at least need something on the bottom counteracting that. But you could load something like right now, if this is attached to the table and I push this way to shear it, it would be in equilibrium, and it would have stresses you could calculate, but they wouldn't be equal to, like the yx stress wouldn't be equal to the traction I'm applying there, because it doesn't meet the requirements of a stress tensor, of a stress element. Okay, so that's about it for that. Now we're moving on to what I called that objects loaded like a big stress element. Okay, now we're going on to beams, and that's a good place to stop for the day. Beams are going to go on for a long time. And so the internal loads that we calculated in statics, the internal tension, shear force, and bending moment, each one of those, and also torsion, which we haven't talked about, but we'll introduce that, produce a certain kind of stress. And so one by one, we're going to calculate how to calculate the stresses for each of those kind of internal loads. And then you take all of those stresses, add them up, and it gives you the total stress. So that's what we're going to be doing over the next several weeks. Okay.